είναι προς τα πάνω. Τώρα είμαι εντάξει. Okay. So this is carrying on. Okay. With
everything is working with camera.
Okay. So good afternoon. We're a bit delayed by 10 minutes. We were scheduled to start at 1 o'clock. This part of the presentation of the court makes reference to risk in relation to new marine fuels, but utilizes the conventional approach to risk assessment with some adaptation with regard to LNG bunkering in some areas. Not very extensive reference to it. The most important part is to understand the concept of formal safety assessment approach, so-called FSA, with regard to the risks involved in dealing with new marine fuels. So I make a reference to what is known as a generic risk. The concept is that when we talk about risk, we must appreciate it is important to understand the frequency of events and the consequences, so we can look at the two extreme parts, and we can say that we have some events which are very rare, but they have very high and dire consequences. At the same time, we have some events which are more frequent, but they have lesser consequences. So, in any case, what we're dealing with is with risks which can be classified at different levels, depending on the combination of the frequency of occurrence of accidents and the level of the impact they impose either on property or the environment or on humans. With regard to LNG bunkering options, we can, for example, we can see that there are risks involved, whether we have a vessel-to-vessel bunkering technique or whether we're dealing with a terminal tank-to-vessel technique, or track-to-vessel, or even a portable tank-to-vessel that involves the transfer of a portable tank to the vessel, and when the tank is empty, then we just replace the tank. So back to the definition of risk, it is important to understand that risk is the combination of hazard probability and its consequences. Now, when we talk about hazard, we're talking about condition which has the potential to cause an accident. It can either be phrased and expressed in terms of probability terms or frequency terms. And one form of presentation of risk involves the risk matrix, where we can distinguish different levels of probability of occurrence and different levels of consequences. So we have a region of higher risk, which is at the top right-hand corner in this example, and we have some intermediate levels of risk, and then we can go to the lower levels of risk, which here shown with a green color. Again, what we just presented, if we were to classify the probability and consequence in a qualitative term, in a qualitative ranking between 1 and 5, we can produce a risk matrix which looks like what we're seeing here, and we can distinguish between high risk regions, intermediate risk regions, and low risk regions as shown with the gray color, as opposed to the other extreme, which is red. It is important also to note that there are regions which present an equal risk, but not the same risk, because in terms of combination of probability and consequence will give us the same number, namely 20, for example, but that can be a combination of a high probability and a lower consequence, or a higher consequence and a lower probability. So it is important to be able to distinguish between equal risks, which are not necessarily identical, in the sense that they're not produced by the same combination of probability and consequence. That is very important at a later stage when we have to look at risk control options. In any case, if we want to reduce risk, we can either look at the lowering the probability or frequency of the hazard or causes the risk, or the consequence, or a combination of both. This can be done in a matter of priority, depending on whether, as I said before, a specific risk is the result of a high probability. There is a possibility that we might have a higher margin in terms of reducing the probability than we have in reducing the consequence, and vice versa. So these are aspects which have to be assessed in order to decide on how to reduce risk. There are therefore some regions which can be identified as being of unacceptable risk levels. A risk level and region which may be defined as being the tolerable region, provided that the risk reduction is impracticable or cost is grossly disproportionate to the improvement gained. And then we have the low risk region, which can be considered broadly as an acceptable region of risk, and something which we can live with. This is again looking at what was mentioned before. If we have to reduce risk, if the risk is at an unacceptable level, looking at a high risk region, or is within the alarm region, as we mentioned earlier. In other words, it lies within a region where control of that risk is subject to some other criteria in terms of cost effectiveness. And then we'll have to look again how to go about it in terms of either reducing the consequence or reducing the probability of the risk, or sometimes we should look at doing both. Now, these regions of acceptable, non-acceptable risks can be also in a more quantitative manner be defined by the so-called FN plots, where we can see the consequences. In this case, we're talking in terms of fatalities occurring as a result of some events. There's a cumulative frequency of events which has, of course, as a result, a number of fatalities. And when you plot the result of such an approach, we come up with a so-called FN plot. And on this plot, we can distinguish the areas where mainly where the alarm region lies, depending on criteria of acceptance, a number of fatalities which may be of acceptable risk. If we are referring to fatalities as it is in the case in this example. And this is what I just described, is something which looks as we see it here. So we can distinguish the unacceptable region. The alarm region here is termed conditional because, as we said, the as low as practicable risk controlled risk is a conditional risk subject to effectiveness of the control or costs and critical parameters of that kind. And then we have an acceptable region as well. Now, there are some examples here of some LNG explosions, but I don't think it's very interesting to look at it now, probably later. Okay, this is something which is known to people who are involved in FSA, in the formal safety approach, but it's important to reiterate concepts. Where we say current approach is not really the current approach as such, it's mostly conventional approach. It's a reactive approach. In other words, we expect something to happen and then we come around and we decide how to improve the situation, how to improve this risk, which is the product of some negative occurrence, such as an accident. And then we have a recommendation of what actions to take. As I said, the so-called current or conventional approach is mainly reactive. There are many disadvantages in carrying out risk control through this approach because usually it takes the industry by surprise. All decision making is made under the pressure of the social media regarding some loss of life, a shipping accident or some major pollution. So it is much better to apply the so-called formal safety assessment approach because we look at risk in terms of the potential of something to happen. What might go wrong is a very interesting question which has to be answered, and this relates to hazard identification. How often, how likely, and how bad, this is all part of the risk analysis, which we just mentioned in terms of the frequencies and probabilities of hazards and their consequences. Again, we can talk about risk control options, as we do in a conventional approach. There is a very important step here, which is called the cost-benefit evaluation step. We put some numbers here in terms of how much this control costs, and whether the benefits we achieve are really satisfying the criteria of cost effective. And finally, again, in order to be assistive in terms of policy making in order to aid decision making. We make a recommendation on the actions which have to be taken, but in a hierarchical approach in terms of classifying the so-called risk control options, classifying them in terms of their cost effect. Again, it's a recommendation, it's not something which is compulsory in terms of its approval and application by the decision makers, whether it is IMO or some other ruling body. In any case, we're talking about structure and systematic methodology, as is mentioned here, in order to develop to assist, rationalize, facilitate, and the key word is the proactive risk control as opposed to the reactive risk control which takes place in shipping operations. Questions and answers. Okay, what can we do about it? Okay, we apply risk control options, as I mentioned earlier. Does it work? An analysis of risk reduction potential of the RCO. We have to see whether this lowers the risk and what is the risk in the reduction which is produced, and whether it's worth it. In other words, we have to measure and somehow evaluate the costs and the benefits which are involved in the risk control. Again, the different steps involved in the FSA approach. This is something which is well publicized by classification societies. This is standard, but it shows a clear classification and presentation of the steps involved. Okay, there is a so-called preparatory step prior to step number 1. The arithmetic does matter here in the steps. I suppose it doesn't make any essential difference, but this is not. It's just a preparatory step to be followed by step number 1. Anyway, we have to define the purpose and the objective of the FSA study, and reference to what we're looking at in terms of a particular ship type, if it's necessary, its size, what accident categories are relevant to this ship type and ship size we're looking at, the operational conditions, some sort of an identification of the problem. Again, the various risks, which, as I said before, we do appreciate that they must be classified as risks to property associated with a potential for property loss, whether this loss is with reference to the ship, either the ship itself or the cargo it carries, with regard to damage to the environment, any type of damage. Most importantly, though, damages which are associated with accidents as opposed to operational damages. Otherwise, probability of occurrence might be continuous. It hasn't got so frequency as accidents do. And then we have to look at potential for damage, loss of life or injury to persons involved in the operations or in the proximity, or they are in the proximity of some activity taking place relevant to ship. There must be some risk acceptance criteria, as we mentioned before. Some risks are acceptable because they're very low and we can live with them. Some of them are not acceptable and some of them are conditional. In other words, we have to investigate whether it's worth taking some measures, some control. Data collection is very important. Any reference to previous records regarding accidents, but also incidents may be also a source of importance, very useful, in order to arrive to some conclusion with regard to whether risks here, we have potential risks because a lot of incidents are only a step away from becoming accidents, and this is very important to look at. Identification of all conceivable and relevant hazards. Okay, so, and as I said before, hazards are conditions which have the potential to cause harm, in other words, to cause some sort of accident which has some consequences either on people or the environment or property. With regard to the proactive control of risk, the key word here is conceivable because that caters for the fact that some risks we have no previous record or we might have very limited historical record, so we have to sit down and decide whether there might be possibility of something like this occurring in the future, and this is based on a conceptual basis, but it's something we have to look at because it's very relevant to the proactive control of risk. In order to do that, we do need a multidisciplinary team, selection of experts, providing the required expertise from all fields of science in terms of being engineers or naval architects, but also can talk in terms of psychologists because human issues are very important here when they relate to human factors and human errors. So it's a brainstorming exercise in terms of everybody coming together and sharing their thoughts about how can a hazard occur and what will be the factors which will create foundations leading to such a hazard and possible consequences. In any case, it is a structured approach. Possible scenarios, yes, we have to look at what I just said, what could be the outcomes of various identified hazards, the causes of the hazard, the measures which can either prevent or alleviate hazards, and we look at again at the probability and the severity of the hazards and the scenarios, in other words, again the consequences, and the ranking of the hazards scenarios by associated risk. Now, with regard to risk assessment, various methodologies which slide. One of them is the so-called fault tree analysis. It is, as we say, an effect-cause approach. We look at the effect first, we have the outcome, and we look at what it caused it. This is very important. It's a top-down approach. Usually we don't know the frequency of the occurrence, in other words, the effect, but if we know the probabilities or the frequencies of the causes that lead to that effect, then we will be able to find the probability of or the frequency of the effect itself. In other words, of an undesired event, such as an accident. Cause and frequency analysis with regard to what we just said, more or less applying a very simplified fault tree analysis approach. Okay, we look at an effect there, which is an accident. In this case, we have an explosion and a fire at an LNG bunkering terminal. We don't know how often this can take place, either because we're dealing with a new application that is, as it is the case for LNG bunkering. There's not many LNG bunkering terminals around the world, and we can approach and evaluate probability or frequency of this event by knowing the occurrence of the causes of it. In other words, the presence of an ignition source. Of course, in order to have explosion and fire, you need to have air around. You have to have some sort of fuel present as well. So in that case, we're looking for a gas leak. And as we can see, in order to have an explosion and fire at the LNG bunkering terminal, then we need all these three causes must be present. Therefore, knowing the probability or the frequency of occurrence of these causes, then we can estimate what the probability or the frequency of the explosion and fire at the LNG terminal is. Of course, for all three to be present, the implication, looking at the old Boolean logic here, this AND gate, as we call it, it will be the multiplication of all the causes will give us the probability or the frequency of occurrence of the undesired effect at the top. Now, if we don't know what the frequency or the probability of the ignition, of the presence of the ignition source, like in this case, we have to look further down what can be the ignition source, and the ignition source could be the result of some sort of human error. In other words, somebody approaching the area bunkering terminal while he's doing some electric work, or it might cause a spark, or it could be the result of metal friction. And in this case, we look that either of the two causes for the ignition source are adequate. Either of them is adequate in order to be an ignition source. Of course, there are cases where both of them might be present, but this is the least probable scenario. In other words, you can have an ignition by metal friction, at the same time you have a human error with regard to the approach in the place with a cigarette. but this is the least possible scenario. We are interested in the most probable scenario, and the most probable scenario will be that one of them can happen, and knowing the frequency of either the human error or the metal friction occurrence, then we can decide what is the probability presence of the ignition source in the area. In this case, the terminal we already mentioned. Again, with regard to frequency of occurrence of a gas leak, if we don't know how often this happens in a site like this, then we can go a bit further down and see what can cause this, and we probably are lucky enough to know the frequency of pipe rupture or some sort of valve failure. We know that both of them can create a gas leak. Both of them can occur simultaneously, but this is again the least probable scenario. The most probable is that one of them will happen. Could be a third cause as well, but it's not included here. One of them is enough to cause the gas leak, and this is what we are interested in. Now, of course, the frequency of occurrence either of the gas leak or the ignition source, if we're dealing with either cause, and not both causes have to be there, we are talking in terms of Boolean logic of an OR gate, and in this case the probability, the sum of the frequencies or the sum of the probabilities of both causes, either of human error, metal friction, or pipe rupture and valve failure, will give us the required result. That's provided the individual frequencies, of course, are very low. Otherwise, the equation is a bit more complicated. We'll see in a minute. Not much, but simple arithmetic. There we are in terms of an AND gate. What we have the multiplication of the frequencies. Both A and B must occur. Therefore, we have to. This is not a likely scenario, but it's necessary for both of the causes to be there. And in such a case, multiply, and we get the probability of occurrence, frequency of the end effect. In this case is 3.2 times 10 to the minus 6, as opposed to the OR gate, which is, as I said before, either of them is adequate to have an undesirable effect, and in that case, okay, probability of occurrence of the top event, the 7.4 times 10 to the minus 2, is the result of the addition of the individual probabilities of the causes of this event minus the product of the probabilities. If the individual probabilities are very low, then it boils down to less than 1%. Then the probability of the end event, in case of an OR gate, boils down to having the addition of the two probabilities. P1 plus P2 will give us the results, because what we subtract will be very, very low. Event tree analysis is another technique which we use for risk assessment. In this case, we go the other way. We have a cause. We're looking at the outcome, at the effects. We identify the consequences and probabilities of combinations of events. This is what we have: an explosion and fire at an LNG terminal. Let's see what the consequences will be. Depends on what what is involved between the explosion and the final outcome, which is the consequence. We might have a firefighting failure. If we don't have a firefighting failure, then we may have some injuries and damage as a result of the explosion and the fire. If we have a firefighting failure, then of course, if there's no an evacuation, if there's no evacuation procedure in place, or some sort of failure occurs in the evacuation, will result in some injuries and serious damage as a result of spreading of the fire. So that's the difference in the final outcome. And if we do have an evacuation failure, then we have loss of life. We may have loss of life and serious damage, which is the worst case scenario in this case. So we start with the event or the accident case, and we look at its consequences, and we develop different scenarios with regard to consequences, which might be, we said before, in terms of human loss or injuries, damage to property, or damage to, and it looks like something like that. We have some initiating event, as in the case before I talked in terms of explosion and fire. Here we can see the start of a fire, we have spreading fire, sprinkler failure, people cannot escape, and you see what the outcomes could be, various scenarios with regard to starting with the most desired outcome in case we have a fire, which is the containment of the fire at the bottom here, and we can go all the way up, and we see that we may have multiple fatalities. In that fashion, we can find out what the abilities of these scenarios of outcomes could be. Looking the frequency of the initiating event, then the probability or the frequency of the intermediate events, which will either give us a favorable scenario, or they will give us the least desired scenario, in this case a multiple fatality scenario. Risk control options. Where and how can risk be controlled? It is important to look at the causal chain. As we've looked at it before, with regard to what can lead to some sort of event, such as an evacuation failure or firefighting failure, the explosion, the fire, or even the human error, which may be the initial cause of such an accident. And with regard to deciding on what risk control options to choose, it is important to be able to estimate what the influence will be of the risk control option on the existing risk. In other words, the reduction, the measure which we are examining will produce at the various stages, because we may have a risk control option which can cater for human error, and that will give us a reduction of risk, or cater for the reduction of explosions or fires or at any stage. This will definitely, we hope anyway, that it will lead to some sort of risk reduction. So we evaluate risk and the existing risk with the risk resulting from the adoption of a risk control option, and we find the improvement. Hopefully there is an improvement. Now, an important step with regard to how we can estimate the reduction of risk is to understand that any measure we propose is subject to some sort of reliability. In other words, its ability to function according to its intended purpose. And in that sense, reliability, which is more or less what we are defining here, is the probability that the system can perform its intended function for a specified time interval under stated conditions. So, in order to be able to evaluate the risk reduction of which is offered by a risk control option, it is important to evaluate its reliability. In other words, the probability that this measure will perform as expected. We can talk in terms of system reliability, which of course will comprise individual reliabilities of various components of the system, whether that is the presence of an operator, or we're talking human reliability. It could be some sort of equipment, individual components of a system, in other words, some machinery or equipment which comprises, when we put it all together, the reliability of the system. In other words, we're in a position to evaluate the reliability of the risk control option in order to be able to evaluate the risk reduction the risk control option offers. As I said, we can look at either a system or a device, and we have to look at, when we talk in terms of reliability, we have to estimate the probability of its operation, its ability to perform for a given period of time under stated conditions, what sort of operation it gives us. It might give us a full performance, or it might give us a half performance. It depends what we're looking at. We know there are some mechanical devices like pumps which might not operate at their full performance, but they might be able to operate at 50%. Is that okay for our providing some sort of risk reduction, or is not acceptable? We either want full performance, or we can compromise with some partial performance. This is very important. For what period of time? Because nothing can be reliable forever, so we have to specify time. And under some stated conditions, we all know that a lot of manufacturers quote some reliability data, but and they usually state under what conditions this is valid, but we do know as well that operating conditions can be very harsh, and they can be very far away from what a test bed, let's say, reliability can give you. Okay, and this is particularly important for shipping because the environment is not so friendly, it's very hostile, and that will accelerate a lot of failures, system failures. Okay, the safety of a system is dependent on, but it's not the same as reliability. This is more or less apparent, we know that. safety is a function of reliability, but it's not the same thing. Now, as I said before, we have to look at the various stages. What makes a system reliable will depend on its specification, its design, its production, the way we operate it, and the way we maintain it. And we do find faults in every more or less stage. We know many times we come up with equipment which may have wrong specifications. Okay, but if we do get the specifications right, then we design it. Hopefully we design it correctly. Sometimes we don't design it according to specification because we do make some mistakes during the design. We might have something good design, but then when we are about to produce it, we don't do it according to the design. So we do production errors, construction errors, in other words, and then the most obvious are faults which occur during operation or during maintenance, or faults which depend on the maintenance level we apply to. As it was already mentioned, the reliability can tell us the probability that the system will work and operate as intended for a specific period of time. Or if we're dealing with many identical systems, then again will give us some sort of information basis of average, which is very important as well, because sometimes individual systems are not representative of the bigger picture. We need to have a lot of data. This is where most of the problems lie in terms of looking at the reliability of a system. And it's equally important to have some sort of indication of the reliability on the basis of a specific system, as I already mentioned, a big number of systems. I'm again saying that we have to embark on this because when we have a risk control option, in order to be able to evaluate the risk reduction which will offer, we must be able to look at its reliability, and we can distinguish in various phases its reliability throughout its life. So we do know, and this applies equally to humans, that as it applies to mechanical systems or electrical systems, that the system reliability can be distinguished in three phases. We have an initial phase, which is a break-in phase. Okay, we decided in order to avert an explosion, let's say in some terminal, to install some new fire extinguishing system, okay, for which we haven't got any data with regard to how it's going to perform. That is the case, because if we do know how this will perform and what its reliability, then we can be very confident about understanding what risk reduction will offer. But if we don't, we must be able to identify that in the beginning that system usually has will offer us a lot of faults, as we say various examples in life. Sometimes a light bulb will break on the first trying to lit it up. And then we go through a period of more or less a steady failure rates, which are very important for us because this is where the item, system, equipment, and to some large extent human beings themselves, they spend most of their time. And we hope, and this is the case, that we have a constant failure rate. It's very important in expressing reliability and how effective it would be, as I said before, to give us the required reduction in risk. And finally, the wear out age, or the aging phase, as we call it, as opposed to the first phase, which is called well as an infant mortality period. Then again, we find out and we discover that fight loads, we have an increase in failure rates. This is not subject to maintenance, by the way. In other words, you can apply as much maintenance as you like, but you still have a very high rate of failure when the item or the system, to be more specific, whether the system is the whole ship or some individual part of it, it goes beyond so-called repair, or it's not worth to repair it anymore. So we have to abandon it and we send it for scrapping. Okay, there are some variations of that, of course. And when it comes to mechanical equipment, we see that things might be a bit more complicated in terms of looking at the useful life, that rate of failure rates during the useful life period might not be so steady, but okay, we can make some assumptions for that as well. It's important to know where we lie in terms of that. These are some of the causes for the break-in. Okay, they are more or less apparent. We know that the initial period failures are basically relevant to poor quality control. We might not have tested the product properly, in other words, prepare it for its operation and some other aspects. This is the most important zone. Working a system overworking it. In other words, whether it's a human being, we start looking at regard to higher than expected loads, we may have issues like fatigue. Whether that is a human being, that's very important, but also something in terms of equipment as well. We might have some random failures as well, unexplained defects. That's true as well in terms of not using it properly. Some item we don't use it properly. We might have some poor design, which comes and the faults appear during the useful life as well. Not necessary to appear immediately in the beginning. We might carry the problem during our useful life of the system. And again, we have some chance and random causes. I would say probably they are very much connected with the unexplained defects. And finally, we are into this zone, which is again limited. It's not very important in any way. It doesn't really cover the same proportion of life as the useful life period. We understand that this is as a result of extended use over time. Now, why are failure rates are important? Because they give us some sort of how do we come up to specify the reliability of the system, as I said, in order to be able to evaluate the risk reduction it will offer. We must be able to distinguish between some operational phases and some non-operational phases of the system. And obviously, when the system is down, is subject to some sort of fault, and it had to undergo some maintenance, okay, so under repair. But we can see through this the failure rates, and this is the important. Okay, so we have a mean time between failures for this case. Where am I? Yeah. In this case, it's simple as stated equation here. So we can have an indication of a failure rate in order to be able to come up with the evaluation of the reliability of the system for either phase of it. In other words, the break-in period or the wear-out period, but most importantly, and this is convenient as well, for the useful life period, the probability density function, very simple in this case, as opposed to some more complicated and involving empirical approaches for the early failures and wear-out failures. You know, the so-called weighable to parameter functions and things like that. So if we do concentrate on the useful life failures, and we do make the assumption of a constant failure rate, then we can talk in terms of mean time between failures, and the probability in that case is very simple. Go back up. Because in that case, if that's the probability density function, then the reliability of the system is E to the minus LT, where L, as we said, is a failure rate, which is 1 upon MTBF. Okay, so it's pretty simple to calculate the reliability of a system for a specified period of time, which in this case is expressed in terms of time parameter T, provided you know the mean time between failures, which you do as well, and they're all both expressed in the same units. In other words, if time is expressed in months, the same must be with regard to mean time between failures. Otherwise, we have a problem. Now, it is also important to be able to calculate the reliabilities of the system in terms of how they are connected operationally, and this is a very simple example which involves a motor, some sort of reduction box there or something, a gearbox, and a pump. Okay, and operationally they are in series, and the important thing is to be able to distinguish by looking at it that it is connected in series on an operational basis, because on a physical basis they might appear completely different. When you look at an engine room, you might see this completely different layout, but you have to be able to distinguish that they are connected operationally. And in that case, okay, if we know the individual reliabilities of the system, then we can evaluate the overall reliability based on the principle that in this case, if any of them fails, the whole thing fails. Therefore, is an end Boolean logic. In other words, all of them, they have to operate from the aspect of reliability this boils down to the multiplication of the individual reliabilities. Okay, so we do that and then we have a break. Okay. All right. So in regard to a parallel system, again we talk in terms of so-called active redundancy here. Both systems operate together simultaneously. In such a case, of course, we have an overall improved reliability. This is the concept of having some sort of redundancy in the system. In this case, a full redundancy, full active redundancy, and it will give us a very higher reliability than the system on the left. Of course, it's always a case of, you can say, this is more or less making very explicit that, okay, if improved reliability of a risk control option boils down to having some improved risk reduction, which I'm sure it will, we have to think about how much it costs. Okay, so this is a question which comes immediately into mind. We do appreciate having a parallel system like the one on the right is much better than having a single system on the left. But of course, there is an increase in initial and operational costs because of the duplication of the system. And then we have, it's not as simple as that. In most cases, we have some sort of connection which involves series and parallel systems altogether, or parallel pieces of equipment. And in that case, we must understand how to approach this. And, this is how we look at the overall reliability of the system. Any of it makes reference to part 1, part 2, part 3, or whatever. But if we're looking at systems, we might as well think that part 2 could be a human being operating somewhere in the system. He's got a reliability of his own, and it could be in series with something else, or it could be in parallel with some other system or equipment. So it's not just mechanical, it's all, it will cater for everything. I think the other one might be more special. Case some special examples. So I think to recap again, if we looking at reducing the risk through the adoption of some risk control option, we should be able, in order to evaluate the reduction in risk, we should be able to evaluate the reliability of the risk control option, whether it involves a single human being, the presence of a human being in a system in order to improve risks, he's doing some sort of surveillance, or it could be some system involving mechanical parts, electrical parts, human beings, or whatever, because that will give us some information about the potential to reduce risk, which is what we need in order to, first of all, decide whether the risk reduction is what we want, is adequate enough, and secondly, to subsequent step, see whether it has any sort of cost effectiveness, which is what FSA is all about. One important step in the whole. I'll leave it here, we'll have a break. Okay. Thank you. This is